VSPER theory continued. What do you do whenever you introduce lone pairs, non-bonding electrons, around a central atom? So what's on the screen is a tetrahedron from an XY4 type from previous play posit. And what you notice here, so Z stands for lone pair of electrons on the central atom. So notice that for this particular grouping, you have a total of 4 bonding groups. 4, 3, 1, 4, 2, 2, 4. So what that means is that for these groups or types of molecules, they all have an electron geometry that is tetrahedral. Okay. But their molecular geometries differ. So what I'm going to do now is draw the structures of the XY3Z and the XY2Z2 types. So what's in red here, that represents a lone pair of electrons. Okay, so Z1, 1 lone pair, Z2, 2 lone pairs, and those are drawn wider because those electrons, their density is allowed to spread out compared to the electrons in a chemical bond. That spreading out causes these bond angles. A reminder that the idealized bond angle for a tetrahedron is 109 degrees, 109.5 degrees in some text. But this lone pair causes this bond angle to squeeze in tighter. Okay. More repulsion. So that causes this angle to be less than 109 degrees. So a lone pair causes more repulsion and will cause that bond angle to be sharper than the idealized 109 degrees in a tetrahedron with no lone pairs. So now what I'm going to do is switch to video and look at these structures in real life. Here's a picture of a tetrahedron. Wedge coming out, dash going back. So the way that you can picture the molecular geometries of the corresponding 4 group geometries is just remove a bond and this little nub is, we'll just say that represents the lone pair of electrons. So the lone pair of electrons, we're now at the second structure, that XY3Z type, still exerts its repulsive forces, keeping these bonds pointing downward. But this is a trigonal pyramid. Again, tri because of the 3, but it's a pyramid. See, those bonds are bent downward. And it looks like the cap of a pyramid, the roof or the top of it. And the lone pair still exerts its force, a little bit stronger. It keeps those bonds pointed downward. Where the bond that I'm holding is on a straight line, wedge, dash. Now for the bent geometry, move that bond. You can see that's bent. So, getting that wedge, dash. If I take and rotate it towards your eye, you can see that bent. It's like if you took a straight line and just bent it. It's not necessarily a creative name, but it's descriptive. And that's what you're left with when you have an XY2 Z2 molecule. Predicting molecular polarity, so whether or not a molecule is polar or not. here I've got 3 examples. They're all AB4 types, or excuse me, XY4 types, meaning one central atom and then 4 atoms bonded around them. You can see that. So determining polarity depends on 1, the presence of polar bonds, and 2, the molecular geometry. So those 2 things. So on paper or on a screen, it's difficult to determine whether a molecule is going to be polar or not, because, well, this looks like that the molecule is flat and that you've got, for a tug of war, for this particular example, you've got a chlorine on the left, chlorine on the right. You would predict that they're going to cancel each other out, and that all the molecules on the screen are nonpolar, is what you would predict if you didn't look at the molecular geometry. However, if you look back at previous play posits, these are all tetrahedral. Okay? They're not flat, they're not planar, they're 3-dimensional. So, polar bonds. This doesn't have any polar bonds by most definitions. So, this is going to be nonpolar. This has polar bonds. Fluorine's more electronegative than carbon. This has polar bonds. Chlorine is more electronegative than carbon. So these 2 pass the first test. But then the second ones, we have to look at the geometries. We have to look at the molecular geometries of both. For that, it'll be easier to see using a model. Here are the models of carbon tetrafluoride and dichloromethane. So, the molecule on the left corresponds to the drawings above. So, carbon tetrafluoride has 4 polar bonds. Fluorine's more electronegative. But if you look at this, if you were to pick this molecule up, picture a tug of war. You've got 2 bonds pulling to the right, 2 bonds pulling to the left. So if you were to picture this as a tug of war, the fluorine atoms are equal in strength, equal in electronegativity. So this side that I'm squeezing, this side I'm squeezing, are equal in strength, and those polar bonds, they cancel each other out. There is no net dipole moment for this molecule because this side can't overcome this side. It's a stalemate. That molecule is nonpolar even though it has polar bonds in it. This molecule, the green spheres represent chlorine, the white spheres represent hydrogen. Chlorine is more electronegative than hydrogen. Same idea. Got a polar bond here, polar bond here. So there is a net dipole moment to the right, the way that I'm holding this. These bonds are nonpolar. They are not able to oppose, or there's no separation of charge on this side of the molecule. This molecule is polar. You might ask how that would look like. Matching the drawing. Again, that's a tetrahedron. Chlorine here, there. The dipole moment be coming toward the camera. is a polar molecule. The polarity of a molecule, again, depends on two things: having polar bonds present and the shape.